Hey everyone, hope you are having a nice time. In this tutorial, you will learn about depth first search. This depth first search is an algorithm and it is related to graphs. So before we begin, let us first go through some of the very basic concepts of graphs. Okay, so graph essentially has two components. They are known as nodes and edges. So graph will essentially have a lot of nodes and these nodes will be joined by edges. Okay, so that is pretty much clear and that is pretty much obvious. Okay, so what is depth first search? Depth first search is a traversal algorithm. What do you mean by traversal? What does it mean? Traversal means that to visit every node of a graph in a sequential order. And what exactly is that order? That order will be defined by the kind of algorithm we are using, and in this case it is depth first search. Okay, so that is mostly the introduction you need to know before we begin. Okay, and this video is broadly divided into three parts. First, I will let you know about the logic behind the depth first search. Then I will let you know the pseudocode. Then we will jump to the C++ implementation. So without wasting any further time, let us jump on to the logic part. Okay, what do we have here? We have a graph which is made up of 8 nodes and 7 edges. Fair enough. Now, what do we have to do? How to perform depth first search? Okay, for that, we have for all the unvisited nodes, we need to perform a depth DFS visit, that is depth first search visit. And what is this DFS visit, you may ask? Okay, so DFS visit means that for every current node, you have to recursively visit all the nodes which are adjacent to your current node. Hmm, sounds very pretty much unclear if put it in words. So why not use this graph as an example and perform DFS? Okay, so this whole thing that we have over here is our graph. And where do we begin? It says that for all the unvisited nodes. But as we can see over here, none of the nodes are visited. So let us arbitrarily choose any point, any node and start from there. Okay, in our case, let us begin from node number 1. Okay, we are on node number 1. And what do we need to do further? It says that visit all nodes adjacent to current node. Recursively visit all nodes adjacent to current node. Okay, so which all nodes are adjacent to current node? Current node is 1 and we have adjacent node as 2 and adjacent node as 3. So which one do we visit? Let us suppose we visit 2. Okay, from 1 we go to 2. Hmm. Now, node 2 has two further ways to go. Either it can go to node 3 or it can go to node 4. It also has node 1 as the adjacent node, but node 1 was already visited, so we won't be moving over there. Okay, let us suppose that we go to node number 4. Why are we assuming that from 2 we go to 4? Can't we go from node 2 to node 3? Yes, we can. This all depends upon how the nodes have been stored in the adjacency list. Okay, so that we will see in our later parts in our pseudocode and also in our C++ implementation. We will see that how adjacency list is made and maintained. Okay, from 4, we have two choices, that is node 2 and node 6. Node 2 is already visited, so it won't be any point visiting it again, so we go to node 6. Okay, from node 6 we have node 4 and node 5 as adjacent. Okay, but 4 is already visited, we go to node 5. As you can see, node 5 is kind of a dead end. We have reached a dead end and we have nowhere to go. So what do? We return back. Okay, we have returned back. Now 6 doesn't have anywhere to go. So we return back to 4. Similarly, we return back to 2. Okay, now you may remember that we had two choices when we were in 2. That is either to go to 3 or either to go to 4. Now we have completed the whole path from 4 and we have reached back to 2. Okay, and now we have node 3 remaining to be visited. Okay, so what should we do? We should visit node 3. Okay, Now, once we have visited node 3, it has two nodes at its adjacent. That is node 1 and node 2. Over here and over here. Okay. So node 1 is already visited, node 2 is already visited. So we won't be performing any recursive visits from node 3. We will just return back to 2, and from 2 we will return back to 1. Now you will again remember when we started with 1, we had two choices, that is either to go to node 2 or to go to node 3. We have completed the whole part from node 2, but what about the path from node 3? As we can see, 3 has already been visited when we were at 2. So there is no point for visiting 3 again. Okay, so this is the first thing we come to know, that in DFS we visit every node once and only once. Okay, so this whole component has been visited. What about these two guys over here? Okay, what about them? Hmm. So again we come to what I said earlier. For all the unvisited nodes, perform a DFS visit. So node number 1 to 6 have been visited. Now it's time for node 7 and 8. Okay. So we again arbitrarily choose node 7 to perform DFS visit. Okay. Node 7 have only one choice, have only one adjacent node. Okay. So we come to node 8. Node 8 is again dead end like node 5 we had earlier. Okay, so we don't move anywhere further. We just visit, we come back, and this whole of the nodes from node 1 to node 8 have been visited. So that was pretty much the logic behind the depth first search. Hope it is quite understandable. Now let us jump to the algorithm part. In the next part, I will show you the pseudocode behind the algorithm. We will just try to derive the pseudocode from what we have said just now, from the logic we have used just now. Okay, jumping to the algorithm part. What do we have over here? We have the same previous graph which we made earlier, consisting of 8 nodes and 7 edges. And as I have said earlier, we need to keep track of which nodes have been visited and also which nodes have not been visited. So it seems pretty much fair to use an array. Let us call it as vis. Okay, short term for visited. Okay, let us use an array vis. And what does this array do? This array will store two elements, either 0 or 1. Hmm. What does this mean? Vis 0 will mean that the node is unvisited. Okay. if okay, let me reiterate. If vis I is 0, it means that the node I is unvisited, and if vis I is 1, then it means that node I is visited. Okay, seems pretty much fair and pretty much easy. And as you can see, in this array we have used indexing from 1 to 8. We have used the zero based indexing, but in C++ implementation it would be zero. In this we have used 1 based indexing, and in C++ implementation we will be using a zero based indexing. So we need to keep that thing in mind for converting 1 based indexing to 0 based indexing, as it is quite important. Okay, and I have just written the logic which I have said earlier, that for all the unvisited nodes perform DFS visit, and DFS visit means to recursively visit all the nodes adjacent to the current node. Okay, that is that. Okay, so we have actually used this thing visited array to implement this. But what about this adjacent to current node? How do we know which node is adjacent to the current node? For that, we will maintain an adjacency list. Okay, the adjacency list over here I have already made. So what is this? It means that node 1 has 2 and 3 as its adjacent. Node 2 has, this node 2 over here has 4, 3, and 1 as its adjacent. 4, 3, 1. Okay, node 3 has 2 and 1 as its adjacent. Node 4 has 6 and 2 as its adjacent. Node 5 has only 6 as its adjacent. Node 7 has 8 and node 8 has 7. So that is pretty much the adjacency list. Okay, now let us come to the pseudocode which I have written over here. Okay, so I have made the pseudocode using this logic only. It is not very much pretty big deal. Okay, so what is this pseudocode? This is the DFS method. Okay, and what does it say? It says that for every I in range of 1 to n, it means that for all the nodes. Okay, if this I is 0, that means if the node I hasn't been visited yet, then what do? We perform DFS visit of I. Okay, seems pretty much easy, seems exactly what I have said over here. Okay, so what is this DFSI? Let us see over here. I have written the pseudo code of the method DFSI. Okay, so DFSI basically implements this part of the logic. DFS visit means to recursively visit all the nodes adjacent to the current node. So DFS visit I over here, we will pass the node number I to the method. Okay, so what do we do first of all? First of all, we set DFS, we set viz I equal to 1, which essentially marks that ith node has been visited. It is the most important step because if we miss to mark something as visited, we may visit it again and again and again, and we may get stuck in an infinite loop. So do not miss this part. Okay. Now, what does this part mean for j arrow adji? It essentially means that for each element j, for each node j, which is in the adjacency list of node I, if that j has not been visited yet, perform DFS visit of that jth node. So that is recursively calling this method again. Okay, seems pretty much easy, seems pretty much fair. Okay, so the pseudocode is done. We have used the logic to perform the pseudocode, and I have also explained the adjacency list. So why not use this graph over here which we have previously used to see whether this pseudocode performs the way we want it to do, like the way it did over here. hmm Let us begin. So first of all, what do? We use the for loop. So in the beginning, okay, before beginning that, we need to set all the members of visited array as 0. Why? Because before beginning the algorithm, all the elements are unvisited. So we set everything to 0. Okay, everything has been set to 0 and we are all ready to begin with our DFS. Okay, now our I is equal to 1. Hmm, I is equal to 1. Okay, what do? This I equals 0. Yes, it is true. This part is true because I have not been visited yet. So what do? We perform DFS with I. Okay. In DFS with I, first of all, we will set with 1 equals 1 because I in this case is equal to 1. So what do? We set it to 1. We are over here. Okay, I has 2 and 3 as its adjacent. So we, for all the element which are in adjacency list of I, in this case I is equal to 1, we jump to j. If that node isn't visited, so is 2 visited? No, it isn't visited. So we perform DFS base of 2. Okay, we come over here. Okay, 2, similarly we will set 2 to 1. Okay, and 2 has 4 3 1 as its adjacent, so from 2 we will first move to 4, set with 4 to 1. Then from 4 we have 6 and 2 as its adjacent, so for from 4 we will go to 6, we will set 6 as 1. Then from 6 we have from 6 we have 5, we will go to 5, we will set 5 as 1. Okay, 5 is the dead end. We will return back. We will return back. We will return back. Okay, we have come to 2. 2 has node 3 as its adjacent. So, what do? Is 3 visited? No, it isn't visited. So, we go to 3. Set 3 as 1. 3 has nowhere to go. 3 has node 1 as its adjacent. 3 had 2 and 3 has 1 as its adjacent, and both of its adjacent node is already visited. So we do nothing, we come back, and from 2 we come back to 1. Okay, we are over here, and as you can see, 1 has 2 and 3 as its adjacent, and we have performed DFS for 2, but we can see that 3 node 3 have already been visited, so we won't be performing DFS for 3 visit DFS visit for 3 again. So we will just return back to where we were calling the function DFS, that is this point over here when our I was equal to 1, this for loop. Okay, so now what do we do? It is very much pretty much clear. As we are in the for loop, we will increment I is equal to 2. Is 2 visited? We will check over here if this 2 is equal to 0. No. Okay, do nothing. We will set I is equal to 3. Okay, is 3 visited? Yes, 3 has been visited. So this statement will be false. We will do nothing. We will just increment I. Similarly, from 4 to 5 to 6. Now we have I is equal to 7. What do we have over here? I is equal to 7, and if with 7 equals 0. Okay, is it true? Yes, it is true. Then perform DFS with of 7. Then again it will follow the same thing, same old story. Okay, set with 7 as 1, 7 has 8 at its adjacent, go to 8, set 8 as 1, return back, and then return back to the calling function. Okay, again over here, increment I is set to 8, 8 is visited. Yes, it is visited. This statement will be false, then we won't be doing anything. I will be equal to 9, and as soon as I becomes 9, we break out of the loop. So we did the dry run of the pseudocode, and I guess the logic is pretty much clear. And this part we will be utilizing in our C++ implementation. That was pretty much the algorithm and the pseudocode of the depth first search. So without wasting any further time, let us jump into the C++ implementation. Okay, what do we have over here? We have the DFS viz, we have the main DFS function, and we have the main function, that is the driver code, which we'll be using to create an adjacency list. Okay, we will take input n, which will represent the number of nodes. Then we will take input e, which will represent the number of edges. Then we will be forming an array of vectors, which will basically mean that adji contains vector of all the adjacent nodes to I. Okay, so basically adji is the adjacency list of I. Okay, then we have visited array to check whether node I is visited or not. So this is the initialization part. We first of all set everything to 0. Then what is this? This is basically making of the adjacency list. Okay, what does it mean? For it means that for all the number of edges, for each edge we will have two things, node u and node v. These u and v are basically the nodes which whose edge is between them. Okay, so we take u and v as input, and what do we do over here? In the adjacency list of u minus 1, we insert the node v minus 1, and in the adjacency list of v minus 1, we insert the node u minus 1. Why minus 1, you may ask? Like I have node u and v as adjacent. Why are you using node u minus 1 and v minus 1 as adjacent? As I have said earlier, that u minus 1 that we have zero based indexing in our C++. Okay, so when we have u, we convert it to u minus 1 to convert it to zero based indexing from one based indexing. Okay, because the input we have over here is of one based indexing. Okay, then what do? We call the DFS function. This DFS function is basically the C++ version of the pseudocode, you can say. Okay, so we are using the for loop from 0 to n, 0 to basically n minus 1. If node I has been visited, haven't been visited, then perform the DFS with of I. Okay, so our DFS method, our DFS function over here takes three input as parameters. It takes the whole of the adjacency list, the number of nodes, and whole of the visited array. And the DFS viz over here takes the node number which we want to visit, the adjacency list, and the visit and the whole of the visited array. Now coming to the void DFS viz. Okay, so as I have said, it takes the ith node which we want to visit, the adjacency list, and the visited vector. And over here we are setting that the node I has been visited by marking viz I equals 1. We perform a print statement, that is C out I plus 1. Why I plus 1? Again, all the nodes were stored in 0 based indexing. Now if we want to print, we will print in the 1 based indexing because the input wasn't that way. Okay, fair enough. Now what does this mean? Auto j colon adji. It essentially means that for each element j which was in the adjacency list of I, okay, so again I'm iterating, for each element j which was in the adjacency list of I, if that jth node haven't been visited, yet, then recursively perform DFS visit. Okay, again pass the jth node, adjacency list, and whole of the visited array. So this is pretty much the C++ implementation. Let us run the code. Okay, I have this as the input. So this input is basically derived from the graph over here. Okay, so we have 8 nodes, 7 edges, and these pairs denote the pair of nodes which have edges between them. Okay, let us copy this input and paste it over here. And yeah, as we expected, the output would be 1 2 4 6 5 3 7 8, like we had over here. 1 2 4 6 5, then back again 3, then again back to 2, back to 1, then 7 and 8. Okay, so that was pretty much the C++ implementation, and that was pretty much the DFS. So as I have said in the beginning, DFS is the traversal algorithm. So does any other traversal algorithm exist? Yes, it does. There is other traversal algorithm named as BFS, that is breadth first search. Okay, I won't be going into the details of that traversal. Okay, and where do we use DFS? DFS is quite basic graph algorithm, and it comes handy in implementing various other complex algorithms in graph. It is like the first step to learning the graph algorithms. Okay, and pretty much it can be used if there are a lot of nodes and we want to find whether a node is present or not. We can use DFS, we can run DFS to check. Okay, coming to the time complexity of this algorithm. Okay, so the time complexity of this algorithm is big O of n plus e, where n is the number of nodes and e is the number of edges. Okay, so that was pretty much from my side. Hope you enjoyed the video and happy learning. Thank you and bye bye.